Welcome to solverfy.
Okay, so problem number 62 wants us to figure out the kinetic energy that a proton has to have in order to be able to neglect or to not include its rest mass when calculating its wavelength, if we want its wavelength to be within 1%. So the first thing we need to do is calculate the actual wavelength of it, and in order to do that, we need to know the energy, the total energy of the proton. So let's go ahead and start with the fact that, so the total energy is equal to the kinetic energy plus the rest energy squared. And the relativistic energy term is given by the momentum times the speed of light squared plus the rest mass squared, c to the fourth. So the rest mass energy squared. Now we can rearrange this and put it in the term p squared c squared is equal to the total energy minus the rest mass energy to the fourth. And now we have this for the total energy here. So we can plug that in here, and we get p squared c squared is equal to k plus the rest mass mp, the mass of the proton, times c squared minus mp squared c to the fourth. So now expanding this, you get p squared c squared is equal to k squared plus 2k mpc squared minus, or I'm sorry, plus mp squared c to the fourth minus mp squared c to the fourth. All right, those cancel. So now we have p squared c squared is equal to k squared plus 2k mpc squared. All right, so now we can, let's go ahead and pull out the kinetic energy to simplify this. So, which is equal to, so we get k squared times 1 plus 2 mpc squared over k is equal to p squared c squared. So if we take the square root of both sides, we get pc is equal to k times the square root of 1 plus 2 mass of the proton c squared over the kinetic energy. All right, so the reason we've done all of this is now if we look at the de Broglie wavelength, so we want to calculate the wavelength. So the actual wavelength, we're going to denote lambda 0, which is the true wavelength. So that's equal to h over p. So now we have p is equal to, so we have p times c is equal to this term. So if we divide both sides by c, we end up with, and plug in the momentum, we end up with h, the wavelength is equal to hc over k times 1 plus mass of the proton c squared over k, or, oh, and I should say, since we want to know at what kinetic energy the it has to be at, the proton has to have in order to be within 1%, we can say lambda, which is the calculated, the one where we ignore the rest mass energy, is equal to hc over k, where k is the kinetic energy, but since we're ignoring, it would actually be hc over e, because you have E is equal to H. E is equal to HC over lambda. So lambda is equal to HC over E. But we're only wanting to, so that would be the total energy. but we're wanting to ignore the mass energy, so we're just saying only the kinetic energy. So that's going to be greater than lambda 0 because it's going to have less contribution. So this number is going to be smaller, so this number is going to be bigger. And then lambda, we want it to be within 1.01, so 1% lambda 0. So if we look, so that means it's going to be 1% larger within 1% of lambda 0. So now we can plug all of this in and say lambda is equal to hc over k, which is going to be equal to 1.01 times lambda naught, hc over k times 1 plus mpc squared over k to the 1/2. All right, the k's cancel, the hc's cancel. We end up with 1 over 1.01 is equal to 1 over the square root of 1 plus mpc squared over k. So 1.01 is equal to square root of 1 plus mpc squared over k. So we want to solve for k. So now we'll square both sides. 1.01 squared. And then rearrange it a little bit. So we'll move, I'll just do this, is equal to 1 plus, I don't want to skip too many steps for you guys, mp squared over k. All right, so now just move the 1 over that way. So 1.01 squared minus 1 is equal to mpc squared over k. Solve for k, multiply that side by k, divide that side over here. So we get k is equal to, you know what, I just realized I haven't carried a 2. So there's a 2 up here, a 2 there, and I lost it. So again, when you're doing this kind of math, you got to really make sure that you don't miss something like that. So this is supposed to be a 2. Because yeah, you make a mistake somewhere where you forget a number and it just carries you, you just end up going along with it and you end up with the wrong answer at the very end. So you have to be really careful about that kind of thing. So, so k is equal to 2 mpc squared divided by 1.01 squared minus 1, which now we can plug in the numbers that we have, which is equal to 2 times 9.38 times 10 to the 8th electron volts, or 938 mega electron volts, divided by 0.0201, which gives us an energy, running out of room here, 9.333 times 10 to the 10th electron volts, or 933.3, sorry, not 933. 93.3 electron volts. So it needs to have kinetic energy of 933.3 giga electron volts in order to be able to not include its rest mass and still be within 1% of, and still be able to calculate its wavelength within 1%. So now there's a couple more parts to this problem. It wants us to calculate the corresponding wavelength and the speed of the proton. So I'm going to create a new page here. So now its calculated wavelength is just going to be lambda is equal to h HC over, oops, HC over K, which is equal to 6.626 times 10 to the minus 34. Okay, well, here, sorry, it's cutting me off. I'm too high up. I'm starting too high up, so I'm going to start over a little bit lower down. Lambda is equal to HC over K. There we go, that's better. Which is equal to 6.626 times 10 to the minus 34 joule seconds times 3.00 times 10 to the 8th meters per second divided by K. So the kinetic energy that it has, 9.333 times 10 to the 10th electron volts, that number that we just got, we just calculated, times, now we're in joules here for Planck's constant, so we want our energy to be in joules. So 1.60 times 10 to the minus 19 joules per electron volt. And all this, you get the wavelength of 1.332 times 10 to the minus 17 meters, or approximately 133.2 femtometers. All right, so now for its velocity, the total energy, so we're given, so we have to use the relativistic energy term. So this is given by 1 over the square root of 1 minus v squared over c squared minus 1 times mc squared. This is the proton. And then we want to solve for the velocity. So let's go ahead and, so we have k over mvc squared plus 1 is equal to 1 over the square root of 1 minus v squared over c squared. Okay, so now we have 1 over, let's go ahead and do this. Let's combine these. So we have k plus mpc squared over mpc squared is equal to 1 over the square root of 1 minus v squared over c squared. V over c. Rewrite this a little bit. V squared over c squared. All right, so square root of 1 minus v squared over c squared is equal to mpc squared over k plus mpc squared. Now we square both sides. So we square both sides. No, so we'll do 1 minus v squared over c squared is equal to mp squared c to the 4th over k plus mp c squared squared. All right, or we have, bring that over, v squared over c squared is going to be equal to just checking my work here as I go through. V squared, bring that over, is equal to 1 minus mp squared c to the 4th over k plus mpc squared. Multiply both sides by c squared. You have v squared is equal to c squared minus mp squared c to the 6th over k plus mpc squared. Pull out, so now v is going to be equal to c times the square root of 1 minus mp squared c to the 6th over k plus mpc squared. All right, we can simplify this more. C times the square root of 1 minus, we'll pull out an mp squared c to the 4th. That's going to cancel with that guy up top. 1 over k over mpc squared plus 1 squared. Okay, so now we know K, that's this kinetic energy up here. We know the rest mass of the proton. So now we can solve all of this. We can plug all these numbers in. So that's equal to C times the square root of 1 minus 9.333 times 10 to the 10th electron volts divided by 9.38 times 10 to the 8th electron volts plus 1 to the minus 2. So that's 1 over that squared. And plugging in all these numbers, we're going to leave C because we want to express it in terms of C. So this is going to be equal to 0.9995. Write that a little nicer. 9995 C. So 99.95% the speed of light is this velocity it has to be traveling, in which you can approximate its rest mass as 0. Let me just clean this up real quick. This is plus 1, that's to the minus 2. Okay,